So exponential decay works much like exponential growth does. You guys saw this. It's just that instead of like multiplying by 2, you're dividing by 2 or multiplying by 1/2. So you're multiplying by something that's between 0 and 1, and that causes the number to get smaller and smaller. Really good example right now is if you think about those flattening the curve graphs and the graphs that you see of the infection rates, for places that are seeing the infection rates go down, you're noticing the infection rates going down following some kind of an exponential decay rate. So they went up exponentially, and then after going up and flattening out, this part is not modeled exponentially, this flattening out rate. But after it goes through that flattening out, and then it drops down, eventually it goes to near 0, but we're going to find that in the next several months and years, it's not actually going to go to 0. It'll get kind of closer and closer, just like in Whatcom County it is, but it's never actually going to reach 0 infections around for a while, maybe until we get a vaccine. Another case, sticking with that medical theme, where exponential decay happens is how medicine is broken down in your bloodstream. Turns out how fast your body processes medicine is often proportional to how concentrated it is in your body. So when you first take medication and it reaches its highest concentration, the body breaks it down faster at first, and then as the concentration goes down, it actually breaks it down slower and slower in some cases. So this is exponential decay. But again, just like other situations with exponential growth that are often reported and communicated using percent change, percent increase, same thing goes for exponential decay. It tends to be reported and described in terms of percentages, not as a multiplier that's producing that change. And so let's look at this example of a flea medicine that breaks down the bloodstream at a rate of 20% per hour. Of course, this is for pets, hopefully not for people. And so you have to think you're not going to multiply this initial 120 by 0.2, because if you multiply it by 0.2, what you're going to have after that first hour isn't a change of 20%. If you multiply it by 0.2, it's actually going to change by 80%. And so you have to think of it this way. If 20% of the medication is broken down in 1 hour, 80% is what remains. And that's what you actually want to know. How much is in the bloodstream at each point, and is it an effective amount? That's kind of one of the factors that's considered when they're prescribing drugs to fight an infection or something like that, is they want to know at what point does it reach either a possibly dangerous level, that it's released too fast, and at what point does it reach a concentration where it's not really being effective anymore and you would need to take your next dose. So anyways, on this one, if 20% of it breaks down, that means 80% of it is left. So a couple ways you might predict the next number is you could say, well, if I have 120 milligrams in your blood and you multiplied it by 0.2, that's going to tell you how much it's actually going to change by. So that would be 24. So in that first interval, it's going to drop down by 24 milligrams, which would be down to 96. So if you do 120, subtract 24, you get 96. Kind of tedious to find 20%, subtract 20% from the previous value to get the next value. But you could keep doing that. It would go from 96, and the next one, I believe, would be 76.8. So remember, in the next interval, you're doing 96 times 0.2 to get the amount of change. I believe is 19.2. And then you are taking 96 and subtracting 19.2, and you get 26.8. And if you keep doing that, your pattern looks something like this. and so on as you go down. And so you'll notice this is not linear change. Of course, it's exponential decay, it's not linear. And so instead of doing it this tedious way, you might have already realized this in those previous investigations. An easier way to actually do this is if you take 100, or sorry, if you take 96 and divide it by 120. So again, this is kind of tedious. I'd rather do this the exponential way. If you take 96 divided by 120, you get 0.8. There's that 80% remaining. So we could just be multiplying by 0.8 each time, and it would achieve the same result. Okay, and then when you make a graph of those points, you get something that looks like this. And you can see, here it is starting at 120, and you can see that drop. It looks almost linear because it's really not changing that fast, but it is gently getting flatter. And so if we want to write an equation for this, we have our starting value of 120. We have our decay factor, the multiplier, of 0.8. And you get an exponential curve that looks like that. Now, I showed the two ways you could calculate the amount of medication left in the bloodstream after each hour. There's sort of the messier way, or there's the way that's using that exponential thinking, what would I multiply it by to achieve that 20% drop? It'd be multiplying by 0.8, and then our function rule was y, but 120 times 0.8 to the power of x. And of course, that decay factor means that there's 80% remaining after each hour. And the way we found it was using the table that we have, the pattern that we have, and taking one y value and dividing it by the previous y value to get a decimal.